Have you ever looked at a pot of boiling water and wondered what is actually moving in there? It looks completely chaotic, but if you drop a purple crystal into the pot, that chaos reveals a pattern. You'll see ribbons of color shooting straight up. Heat from the stove acts as a physical engine, lifting water from the bottom and driving it through a continuous circular loop. This process is called convection. It's the transfer of heat through the actual physical movement of a fluid. Think about leaving a metal spoon in hot soup. The handle gets warm, but the metal itself stays locked in place. In a fluid, the material actually travels to deliver the heat. Recognizing this invisible loop unlocks the secret to why fluids move all around us, connecting kitchen phenomena to the weather patterns outside. To understand why this happens, we have to look down at the molecular level. When the water molecules right at the bottom of the pot get hot, they start to vibrate faster. As they shake, they force themselves apart. This expansion means the hot water takes up more room than the cooler fluid above it. Because the hot water is spread out, it is less dense and floats toward the surface. Moving away from the heat source, it cools down. The molecules pack closely together again, become heavier, and sink back down the sides. Zooming back out, you get this continuous cycle. Hot fluid pushing up the middle, cold fluid sliding down the edges. This is a convection current. We often hear that heat rises, but heat itself doesn't have a direction. Hot fluids rise because these density differences force them upward. Let's test that rule. What happens to this loop if we heat the fluid from the top instead of the bottom? The warm, light fluid would simply remain trapped at the surface. The heavy, cold water at the bottom would never move up, breaking the cycle and preventing a continuous loop. This is also why convection requires a liquid or a gas. Solid particles are locked in place, so they cannot flow to create a current. When density alone drives this loop, we call it natural convection. Adding a fan or a pump to physically push the fluid around becomes forced convection. Natural convection is a powerful, self-sustaining engine, but its architecture relies entirely on heat being applied from below. You can see this same engine running in your house. A single floor heater can warm an entire room without using a fan. The air near the heater warms up, expands, and hits the ceiling. It travels across the room, cools down, and sinks down the opposite wall to sweep back across the floor. This upward push is exactly how chimneys work. Hot smoke is much less dense than the air outside, so it naturally races up the flue and out of the house. In a building fire, the hottest, most toxic air violently rises to the ceiling, leaving a layer of cooler, clearer air right at the floor. That is why firefighters are trained to crawl. Ernest, this physical rule determines the safest way to navigate a life or death scenario. We can scale this up even further. Step outside onto a sunny beach during the day, and you are standing inside a massive planetary convection loop. Land masses heat up much faster under the sun than ocean water does. This sun-baked land acts just like the stove burner. The air directly above it gets hot, expands, and rises rapidly, leaving an empty area of low pressure behind. To fill that void, the cooler, denser air from above the ocean rushes in sideways. This massive atmospheric convection current is what we call a sea breeze. From boiling pasta to the wind on a beach, convection is the invisible, elegant engine of motion, constantly shaping our world.